Lesson 3, Chapter 3, we're going to be looking at the definition of a mole and then using moles and Avogadro's number to do some calculations. We're also going to explore stoichiometry and chemical equations. First, we're going to start by talking about the mole. So what exactly is a mole? Well, if you remember back from Chapter 1, and we were talking about physical quantities and SI units, the mole was actually the SI unit for the amount of a substance. Mole was actually devised by chemists so that they could count chemical particles simply by weighing them. So how exactly do they do that? Well, first off, they define the mole by using Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd. So they define the mole by saying 1 mole is equal to 6.022 times 10 to the 23rd particles. Now, that word particles can actually stand for multiple entities. So what I mean by that is you can replace the word particles and put atoms, or molecules, or formula units. So in that case, we can say that 1 mole of a substance is equal to 6.022 times 10 to the 23rd atoms, for instance. Now looking at that number, 6.022 times 10 to the 23rd, that's actually a very, very large number. It's in scientific notation, so if we were to represent it in normal notation, we would have to move the decimal point 23 times to the right, making this number extremely large. I don't even know how large. It's more than trillions. It's like gagillions or something ridiculous. So how are we going to use this definition? Well, we're going to use it very similar that you would use the definition of a dozen. So if you know, 1 dozen is usually equal to 12 of something. Now, just like 1 mole is equal to 6.022 times 10 to the 23rd particles, 1 dozen is equal to 12 units of something. So we can replace that word units with multiple things, right? We can say a dozen pencils, and we're talking about 12 pencils, or a dozen donuts, more common, right? You're talking about 12 donuts. So it can be used for multiple different conversions. And the reason I'm saying conversions is because you'll notice both of these, the mole and the dozen, have an equal sign saying what it's equal to. Whenever you have two numbers equal to each other with different units, they can be used as conversion factors. So when we are using moles in calculations, we're going to be using the definition of a mole to solve for it. The definition of a mole being Avogadro's number. So we're going to calculate it the same way that you would use the definition of the word dozen. So let's start by looking at the first example. So the first example asks, how many eggs are in 3 dozen? So the term entities in the definition dozen is going to be eggs in this case. So how would you solve it? Well, you take the number 3 and you multiply it by what the word dozen stands for, and it stands for 12. So 3 times 12, you get 36 eggs. So you're going to do the same thing with the word moles. So if you were asked, for instance, how many atoms are there in 3 moles of a substance, you would take the number 3 and you would multiply it by what the word moles means. In this case, the word moles means 6.022 times 10 to the 23rd. So when you multiply that out, you get 1.807 times 10 to the 24th atoms. Now keep in mind, I'm just showing these as examples on how to do the calculations. I am not keeping with significant figures here. So when we are talking about moles, the entities that it is equal to after the 6.022 times 10 to the 23rd, it can be atoms, just like we saw in the previous example, or it might be molecules, formula units, ions even. So the word entities can be replaced with a multitude of things so that we can calculate a multitude of chemistry-related problems. So Avogadro's number, you'll see in future equations, is often represented with this letter N sub A. Now, when we're talking about 1 mole equaling 6.022 times 10 to the 23rd of something, as we saw in the previous slide, it can be 10 to the 23rd of atoms, elements, ions, photons, right? There's a multitude of things we can calculate. So how do you know which entity or term is being used? That's what this table here is for. If we're talking about 1 mole of an element, for instance, so an element off of the periodic table, then we're talking about 6.022 times 10 to the 23rd atoms. It does not matter what element we're referring to. So if I say 1 mole of oxygen, well, in 1 mole of oxygen, there is 6.022 times 10 to the 23rd atoms of oxygen in 1 mole. If I'm talking about mercury, there are 6.022 times 10 to the 23rd atoms of mercury in 1 mole. Looking at covalent compounds, which we learned about in Chapter 2. So if we're talking about covalent compounds, the term used is molecules. If we're talking about ionic compounds, the term used is formula units. We'll get into photons in later chapters. So let's try an example calculation problem. If we were asked how many moles are in 9.6 times 10 to the 24th molecules of oxygen. So how would we solve that? Well, we would have to do our railroad tracks that we learned in dimensional analysis. It's going to be the same type of calculation, just using the conversion factor where 1 mole is equal to 6.022 times 10 to the 23rd. And in this case, it's 10 to the 23rd molecules is the entity being used. So to solve for this, we would want to start our railroad tracks in that upper left-hand corner with the number given to us in the problem. We then take the conversion factor where 1 mole of oxygen is equal to 6.022 times 10 to the 23rd molecules. Notice we're putting the Avogadro's number, which is attached to the entity molecules, in the denominator so that molecules and molecules cancel out, giving us an answer with just moles. Now in this problem, we are looking at sig figs. So you'll notice in the original problem, if we look before the multiplication sign, there was 2 significant figures. So we want to make sure to report our answer to 2 significant figures. So that's why we rounded it up here to 16. Next, we're going to look at calculating molar mass. Now, molar mass is oftentimes referred to as molecular weight as well, so those 2 terms are interchangeable in this course. So what is molar mass? Well, molar mass of an element is the same thing as the atomic mass on the periodic table. So you can see this little cutout of carbon from the periodic table at the very bottom of the slide. So the atomic mass, the average atomic mass that's written there, that is the molar mass of carbon element. Just 1 atom of carbon. Now, we're going to learn how to calculate the molar mass for compounds, so where there's more than 1 atom present. So in order to do that, we need to sum the atomic masses of all the atoms present in the chemical formula. So in order to calculate, we of course need the chemical formula itself. Some examples are shown here for water, copper 2 chloride, and that's benzene. Remember with chemical formulas, the subscripts give the number of each atom present. So the subscripts being the numbers that come after each atom. So in the case of hydrogen, there's 2. Oxygen, since there is no number present, it would just be 1. The other piece of information you need in order to calculate molar mass is the atomic masses of each element that are represented on the periodic table. So let's look at an example. We're going to look at calculating molar mass for CHCl3. So how do we do this? Well, for each element present in that chemical formula, we want to take the number of atoms present by looking at the subscripts after each element and multiplying it by the atomic mass of that element, and we find that on the periodic table. Once we're done doing that for each element, we're going to add the molar masses of the elements together and then put units of grams per mole. Now the units of grams per mole is very important because this is going to be extremely useful to us later when we're doing conversions between grams and moles. Because since there are 2 units present, grams and moles, we can use it as a conversion factor to get between grams and moles. So let's look at the example. The chemical formula of CHCl3 is shown here. So we like to make a table with all the elements present: carbon, hydrogen, chlorine. So for carbon, looking at the chemical formula, there is no subscript after carbon, so we assume there's just one carbon atom present. We then multiply that by the molar mass of carbon that we find on the periodic table, which is 12.01. Moving to hydrogen, looking at the chemical formula once again, we see there's only one hydrogen atom present in CHCl3. So we multiply that by the molar mass of hydrogen found on the periodic table, which is 1.008. Moving on to chlorine. There is a subscript after chlorine, and the subscript is 3, telling us there are 3 chlorine atoms present. So we multiply that by the mass of chlorine found on the periodic table, which is 35.45. Multiply across and add all the 3 values together, and we get a total molecular mass of 119.37, units being grams per mole. Let's look at some practice problems. Feel free to pause and try these on your own to check your answers. For molar mass, or molecular weight of silicon, so number 1 here, notice this is not a chemical formula. This is an element by itself. So this is the easiest question you will get referring to molar mass. All you need to do is find silicon on the periodic table and find what its mass is and report it with units of grams per mole. So finding silicon on the periodic table, we see that its mass is 28.086. So its molar mass that we would report is going to be, sorry, I'm having technical difficulties, 28.086 grams per mole. And they just wrote it in a conversion factor fraction form. Now, next problem is the molar weight. I should say molar mass or molecular weight, but little glitch there, of HClO3. So for this one, there is a chemical formula. So you need to go through the steps of multiplying how many atoms there are of hydrogen by the mass of hydrogen, how many atoms there are of chlorine times the mass of chlorine, how many atoms there are of oxygen times the mass of oxygen on the periodic table, and then adding all those values together. So here we're showing how that works. So there was one hydrogen atom, so we multiply that by its mass. Chlorine, same thing, one atom of chlorine multiplied by its mass, and then for oxygen, 3 atoms multiplied by its mass. Now I do want to point out the masses that you are seeing on this slide might differ slightly by that last digit, depending on what periodic table you're using. So some periodic tables only go out to 2 decimal places and some go out further. So the slight differences will still get you the correct answer. So calculating this all out, we get 84.455 grams per mole for the molecular weight of HClO3. Last problem, what is the molecular weight of C5H10O5? So this is a big one, right? There are 5 carbon atoms, 10 oxygen atoms, and 5 oxygen atoms. Or sorry, 10 hydrogen atoms and 5 oxygen atoms. So to calculate this one, you would find the masses of each element present multiplied by the number of atoms of each, and then add them all together. So here we have it all laid out, not going in the same order, unfortunately, as above. So it looks like they started with hydrogen here. So 10 atoms of hydrogen multiplied by the molecular weight, 5 of carbon, and then 5 of oxygen. When you add it all together, you should get somewhere in this range, depending what periodic table you used, of 150.13 grams per mole. Chemical reactions. So what are chemical reactions? Chemical reactions occur when chemical bonds between atoms are broken or formed. So you think about it, coming to lab, you mix 2 chemicals together, you get new chemicals out, right? So bonds are broken, new bonds are formed, rearrangement occurs. So chemical reactions contain two general components: the reactants, being the components that are mixed together. So those are the ones that are going to be put in the flask or the beaker or whatever container you're mixing them in. So they're the ones that are going to undergo the change during the reaction. And then, of course, the products, which is what you get out. That's what's formed at the very end, what you isolate, what your desire is. So when we're looking at chemical reactions, we always have the reactants on the left-hand side with an arrow pointing to the products. We represent chemical reactions by using chemical equations. So in this particular chemical equation, our reactants are going to be hydrogen gas and oxygen gas. We then have an arrow pointing to the product, which is water. So let's look at a few features of chemical equations. First off, these little subscripts in parentheses after each one, what do those represent? Those are representing the physical states of the reactants and products in the chemical equation itself. So whenever you see a little S after a element or compound, it means that it was added in a solid form. So we actually took or weighed out solid reactant and added it to the flask. Whenever you see the letter L, that stands for liquid. Now, it's not all liquids that you will be using in lab or in life. The L is only for a pure liquid. So remember when we talked about pure substances back in chapter 1, that means it was just one element or one compound. Okay, so when we're talking about a pure liquid, it's going to be a pure compound such as water, as you can see in the example above. The water has an L by it. It's saying it's water with nothing dissolved in it. So pure water. Now, you might also see, and will often see in lab, the term AQ after a compound. So what does AQ mean? Well, it stands for aqueous, but what it means for us in lab is that it's a solid that has been dissolved in water. So it isn't a liquid form that we're adding it, but it's not pure water, or it's not a pure liquid by itself. It's actually a liquid, in this case water, with a solid dissolved in it. Last but not least, we have G, which just means that it was added in a gaseous form. So in the example above, we had hydrogen gas and oxygen gas being added together to form pure liquid water. Now you'll also notice that there are numbers in front of some of the elements or compounds. These numbers we'll refer to as coefficients. So why are those numbers there? Those numbers are there because whenever we're doing a chemical reaction or representing a chemical equation, we want to make sure that that equation is balanced. So what does balanced mean? It means that there are the same amount of atoms on the reactant side as there are on the product side. So for instance, on the reactant side, if we were to have 4 atoms of hydrogen, we want to make sure that we have 4 atoms of hydrogen on the product side as well. Because whenever we do reactions, we don't lose material. It doesn't just disappear into thin air, right? It's just rearranged into new forms. It's that law of conservation of mass. It's very similar. We're not losing any mass, it's just being converted into different forms. When we balance chemical reactions, which we'll look at a little bit later in this section, we want to make sure that the molecular formulas remain constant. And then, as I said before, the atom count needs to be the same on both sides of the equation. So in the case above, how do I know that the atom count is the same on both sides of the equation? Well, in order to figure out the atom count, we take the coefficient that's in front of each element or compound and we multiply it by the subscript on that element or compound. So when I do it for hydrogen, I would be doing 2 times 2, which gives me 4 hydrogen atoms. Going over to the product side, I'm going to be doing the same thing for hydrogen to make sure that the atom count's the same. So I take the coefficient that's in front of water, because it's telling me there are 2 water molecules, and I multiply it by the subscript that's after hydrogen, which in this case is 2. 2 times 2 gives me 4 hydrogens. So my hydrogen atom count is the same, meaning the hydrogens are balanced. Now looking at the oxygens on the reactant side, there is no coefficient in front of that O2, so we assume the coefficient is just 1. So taking the coefficient of 1 multiplied by the subscript of 2, that gives us 2 oxygen atoms. Moving to the product side to see if the oxygen count is the same, we take the coefficient in front of water, which is 2, multiply it by the subscript after oxygen. Since there isn't one, we assume the subscript is 1. So that gives us 2 times 1 for 2 oxygen atoms. So this chemical reaction, this chemical equation is indeed balanced. So let's dive a little deeper into exactly how we balance an equation. So here we have an already balanced equation, and we can figure that out by doing the atom count. So I have the process written out here. To do the atom count, you want to take the coefficient that's in front of each element or compound and multiply it by the subscript. And you do that on both the reactant side and the product side to make sure there are the same amounts and types of atoms on both sides. So the work is shown below. You can see there are 4 aluminum atoms on the reactant side. When you take the coefficient times the subscript on the product side for aluminum, you also get 4 atoms of aluminum. For oxygen, you take the coefficient of 3 on the reactant side, multiply it by the subscript of 2 after oxygen, and you get a total of 6 oxygen atoms. Going over to the product side, you take the 2 that's in front of the aluminum oxide compound, and you multiply it by the subscript of 3 on the oxygen atom itself to get 6 oxygen atoms. So it looks like the atom count is the same on both sides. When you are balancing an equation on your own, so if it's not already balanced and you need to balance it, the coefficients is the only thing that can be changed to balance the reaction. So the number in front of the elements or compounds are the only things you can change to balance the equation. The subscripts cannot be changed. So those numbers in red, you cannot change the subscripts. If you change the subscript, you're changing the compound itself. You are now making a new compound, so you can't do that. What you can do is you can change the amount of the compound that's already in there by adding more of it. That's what the coefficients represent. The subscripts, you're going to be changing the compound itself. So be very careful with that. The next 2 slides are some examples and practice for balancing chemical equations. Now, trying to show how to balance and go back and forth between the reactant and product side on a PowerPoint video is quite difficult. So I'm going to leave this here for you to try to solve on your own. I've included a short balancing YouTube video in the email that I sent out to you. So you can watch that to see how you start from scratch to balance a chemical reaction, and then come back and try these examples on your own to see how it goes. Now, I will give you a hint. When you're balancing equations such as this, whenever you have the same element in more than one spot, so what I mean by that, in this case on the product side, notice you have oxygen here in the compound carbon dioxide, and you also have oxygen here in the compound of water. So if you have an element such as oxygen in 2 different places on one side of the equation, balance that element last. It's going to save you a lot of trouble because usually it'll balance itself out after you balance the remaining elements. So here is the answer for this one. So it's important to make a list of the elements present, and then you just go back and forth doing the atom count, adding coefficients until it is balanced. So to balance this one, you need a ratio of 1 to 3 to 2 to 2. So those are the coefficients that should be in front. For instance, for this 1, if you were to omit that 1, that's fine, because you don't need a coefficient there. If there is no coefficient present, we just assume it's a 1 anyway. So here are 2 more practice problems that you can try on your own. So the first one is taking nitrogen gas and hydrogen gas to form ammonia, or nitrogen trihydride if we're naming it systematically, as we learned with covalent compounds. So the first step in balancing, as you probably saw from the video, is to make a list of all the elements present and then how many are currently present based off of the subscripts given after the element symbol. Once you have that done, then you start adding coefficients to balance so that you get the atom count the same on both sides of the equation. So you'll notice for nitrogen, for instance, since there's a subscript of 2, that means there are 2 nitrogen atoms. Hydrogen, same thing. Now, when you're looking at these, you can tell that the nitrogen and hydrogens are not balanced, right? On the product side, we have 1 nitrogen. On the reactant side, we have 2. So you then need to add coefficients going back and forth until you get the same on both sides. When doing that, you end up getting an answer or a ratio of 1 to 3 to 2. So 1 nitrogen gas molecule, 3 hydrogen gas molecules to produce 2 ammonia compounds. Looking at the next problem, balancing this equation, you can notice that this time we actually have polyatomics. So different than they have shown on these slides, whenever you have a polyatomic, it can be very, very useful. If the polyatomic is the same on both the reactant and product side, do yourself a favor and do not split it up, keep it together. So what I mean by that is this carbonate ion, for instance, it stays together on both the reactant and product side. So looking at this, I can tell that there is 1 carbonate on both sides. So I can keep those CO3s together, just like I can with the nitrate, the NO3s. Doing that's going to save you a lot of trouble, especially when you're trying to balance those oxygens. So once you go through the process, this is the ratio that you would get.